Okay, so as I promised, this morning we'll go over the revision worksheet that's available on stream. That's in week 5, and if you just scroll towards the bottom of the week 5 page, you'll see the resources for revision for the mid-semester test next week. All right, so let's see. We have here the first question. We're given numbers and we're asked to write these in scientific notation. So scientific notation, it's that form where you have a times 10 to the b, okay? And a should be a number between 1 to 9. Between 1 and 9, including, of course, 1 and 9. And then b is the exponent. It can be both positive and negative, depending on where you move the decimal place to achieve a. Okay, so let's look at the first one, 3 million kilograms. It's not explicitly shown where the decimal point is, because if you have whole numbers or integers, it's implied that the decimal point is right at the end. Okay, so when you try to find a, meaning a number between 1 and 9, you have to move the decimal place to the left, and you go 1, 2, 3, 4, 5, 6, so that you have 3. Yeah, that's between 1 and 9 times 10, right? And the exponent b is the number of jumps that you made to move the decimal point. So here you made 1, 2, 3, 4, 5, 6 jumps. Okay, and then finally, to find whether the b is positive or negative, if you move the decimal place to the left, then that will be a positive b. So positive b if moving left, and negative b if moving right. Okay, you moved the decimal place to the left, so that should be a positive 6 for the exponent. So if you have a positive exponent, you'll also see that you have a number that's more than 1, like a big number greater than 1. So for the second example, it's easier to see where the decimal place is. So you move that 1, 2, 3 spaces to the right, so that you have 2.5. Okay. 2.5 is a number between 1 and 9 times 10 to, you moved 3 decimal places, 3 places to the right, and that should be a negative exponent. You can see that if your exponent is negative, then your number is less than 1. Whereas if your exponent is positive, the number would be greater than 1. Okay. All right, so as usual, if you have any questions as we go along, just type them in the chat box. I'll constantly keep an eye, or periodically keep an eye out for your questions and address them as we go along. All right. Okay, so for the next question, write 423 nanometers as a number, not scientific notation, but as a number in meters. So number, this is a number. Okay, in this form, this is scientific notation. What is given to us is prefix form. Okay, so recall that nano is a prefix that you add to the base unit. That's like a shortcut for the times 10 to the exponent. Okay, and nano means 10 to the minus 9. Okay. In the test is open book, so you don't have to memorize the prefixes, but it will be useful to know like this is, I think, lecture, I'm not sure, free fall, lecture 5. Yeah, I recommended, I suggested while we were doing lectures that as we did the lectures, you do like a formula sheet or an information sheet that you can easily refer to during the test, so that will make it easier for you instead of flipping through your notes or opening different slides. So I think that will be useful to do for the test here, summarize equations and formulas that you think will be useful. So the prefix nano means 10 to the minus 9. That means this 423 nanometers is can be written as 423 times 10 to the minus 9 meters. If you expand out the prefix nano as times 10 to the minus 9, and then you do the reverse of what you did for the first question 1B. Yeah, so it's a minus 9, it's a negative exponent, so that gives you a clue that the resulting number should be very small. It should be less than 1. Okay, so you move the decimal place of 423 so that you'll end up with a number that is less than 1. Move it 9 spaces. Yeah, 423 is a whole number. It's implied the decimal place is at the end. Okay, so let me just do this here with more space. So 423 decimal place is implied to be at the end. You have to move it 9 spaces because you have this times 10 to the minus 9. Okay, so you go 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll find you should have 6 zeros before everything here will be filled out with zeros. So writing it down as a number will be 0.60423 meters. Right? Okay, so those are the 3 ways of writing number as a number itself, or of writing a physical quantity as a number itself, like in 1A and 1B, or as a scientific notation, or as a prefix form. And you would be expected to know how to write, convert from one form to the other. Okay. All right, next question, we want to convert 250 kilometers per hour to meters per second. Okay. Whenever you're doing conversion problems, the first thing you need is a conversion factor, because the conversion factor relates the units that you want to convert from and to. Okay, so you want to convert kilometers to meters, so you can have 1,000 meters is equal to 1 kilometer. Right? And hours to seconds. 3,600 seconds is to 1 hour. So this this relates kilometers to meters and hours to seconds. Yeah, once you have your conversion factor, 200, it would be easier to separate the number from the unit. So separate 250 from kilometers per hour. You can go 250 times 1 kilometer divided by 1 hour, separating out the number 250 from the unit kilometer and hour. Multiplying anything with 1 doesn't change the equation, because any number multiplied or divided by 1 is the number itself. But writing it this way can easily you can easily relate your conversion factor to what you want to convert. So you can see here 1 kilometer, you should use that conversion factor and go and substitute 1 kilometer means 1,000 meters. Okay. And then here you can see you have to convert 1 hour, and you can see in your conversion factor that 1 hour is replaced by 3,600 seconds. Okay. And then you carry out the calculation, 250 times 1,000 divided by 3600 is 69.4 meters per second. If it's kilometers per hour, there's a shortcut. Converting kilometers per hour to meters per second, the shortcut is to divide kilometers per hour by 3.6. And that should give you the answer in meters per second. So for example, here you can just go and say 250 divided by 3.6, which should also give you 69.4 meters per second. Yeah, that's special for kilometers per hour to meters per second. And it's coming from the conversion factor. Right, for this next question, you're converting 7,800 grams per cm cube. Okay, the tricky bit here is there's this cube, exponent 3 in the base unit in the units that you need to convert. But still, you start from the conversion factor. You want to convert grams to kilograms, and 1,000 grams is equal to 1 kilogram. Okay, and you want to convert centimeters to meters, 100 centimeters in 1 meter. Right? And then once you have your conversion factors, you go 7,800 grams per cubic centimeter. Separate out the units from the number. Centimeter cube means centimeter times centimeter times centimeter. Yeah. 1 centimeter times 1 centimeter times 1 centimeter is equal to 1 cubic centimeter. Right. But separating out this way means that you need to convert grams to kilograms and 1 centimeter to meters. So looking at your conversion factor, you have 1,000 grams is to 1 kilogram, but you want to know how much is 1 gram in terms of 1 kilogram. If you divide 1,000 grams by 1,000, then you will have 1 gram on the left side, because any number divided by itself is 1. But you also have to do the division on the right side. So yeah, you have to do 1 kilogram divided by 1,000. That's 0.01 kilograms. Okay, so that then gives you the conversion factor for 1 gram. So 1 gram is equal to 0.001 kilograms, which you can now substitute in your equation to replace grams. Yeah, to replace this gram there. Okay, and to replace the centimeters. So centimeters, in your conversion factor, you put 100 centimeters is to 1 meter. You want 1 centimeter instead of 100 centimeters. So if you divide that by 100, and you divide the other side by 100 as well, then you get 1 centimeter is equal to 0.01 of a meter. Right? Then you can use that for replacing centimeters. So 1 centimeter is 0.01 meter. 0.01 meter times 0.01 meter times 0.01 meter. So you have to do the conversion of centimeters to meters 3 times. Putting everything in the calculator would give you, I think the calculator, if you're using a scientific calculator, usually the calculator will give you the answer in significant notation, in scientific notation, I mean. We'll give you the answer in scientific notation if the exponent is more than 3, I think. Yeah, so you can just copy that across, or that's equal to 7,000,02345. Yeah. If your decimal place starts here, 1, 2, 3, 4, 5, 6. but you can leave your answer in scientific notation if you want. It depends on the test. It will be multiple choice, and some questions will ask you to fill in the answers. So it depends on whether you're given choices in scientific notation or number form. Okay. All right, next we have here rearranging the equations. So you're asked to rearrange this equation to isolate VF, right? So I'll use the one I taught in class where you build up the equation and then do the reverse operations to arrive at the isolated equation. So you want to isolate VF, so you start from VF. Okay, your order of operations, bed mass, means that you have to do brackets first. Okay, so in building up your equation, VF plus VI is bracketed. So you have to build that part of the equation first. So you have to add VI in order to recreate that bracketed form. And you have VF plus VI. And then that's when you multiply 1/2 delta T. Okay? So it's 1/2 times VF plus VI times delta T. And when you're doing your multiplication, the order doesn't matter. So you can just put 1/2 delta T VF plus VI. And that gives you the equation delta X. So you can now go back. Starting from delta X, you undo the last thing that you did, which is times 1/2 delta T. That means you have to divide by 1/2 delta T, divide delta X by 1/2 delta T. So you have delta X divided by 1/2 delta T, right? And then undo the plus VI by doing a minus VI. Then you have delta X divided by 1/2 delta T minus VI, and that gives you VF. Therefore, VF is equal to delta X over 1/2 delta T. Okay. Right, next one, isolate delta T. Okay, this is the equation is a bit simpler, so I'll do the rearranging using the second method, which is a normal progression. When usually you've done this building up and tearing down process, you'll sort of start to develop the skill, and you can just rearrange this equation without going through the building up process. So we want to isolate delta T. So delta T is tied up with A and VI via the multiplication and the addition there. So if I subtract both sides, let me just write the equation again. So if I subtract both sides, I subtract VI on both sides. Okay. That eliminates VI on the right side because VI minus VI is nothing. That gives me VF minus VI on the left and just A delta T on the right side. Then A delta T is tied up by a multiplication sign. So to undo the multiplication, you do a division, because A divided by A is equal to 1. Any number divided by itself is equal to 1, but you have to do that on the other side as well. Then you have delta T is equal to VF minus VI over A. Right? Okay, that's the rearranging bit. Okay, the next one here, we're given the positions of the object. So the object started from A. Let's say this is the starting point. And then it went to B, C, D, E, and finally ending at F. And the question asks us, what is the object's displacement? How far away is it from the starting point? And it says 1 square is 1 meter by 1 meter. So this is 1 meter, that's 1 meter. Okay, how do we find the displacement? So displacement, we use delta x. Delta x is how far away the object is from the starting point. And it's a straight line from the end point to the starting point, right? And to start point. Okay, so that means you need to draw a line connecting the endpoints and the starting point. And this is what you need to figure out. What is that distance? I mean, what is that length? That will give you that length will give you the displacement. Okay, so it's diagonal. Okay, it's hard to measure that, but you can form a right-angled triangle using that diagonal line. So if you say connect these points, then you can sort of form a right-angled triangle with the displacement as the hypotenuse of the right-angled triangle. Okay, so the displacement is the hypotenuse of the right-angled triangle. You can figure out what the sides of the triangle is because you're given that 1 square is 1 meter by 1 meter. That means that from the starting point to this point, the horizontal side of the triangle, this is actually 4 meters. Okay. Right. Okay, and for the vertical side, that's actually 3 meters. So you have this right-angled triangle, and you know the horizontal and vertical sides, and you want to find the hypotenuse, and that will give you the displacement. So Pythagoras theorem gives you the relationship between the hypotenuse and the two other sides of a right-angled triangle, right? The hypotenuse, let's just say, yeah, okay, I'll hypotenuse of your right-angled triangle is equal to the square root of the horizontal side squared plus the vertical side squared. So from there, we can calculate the displacement. Displacement is therefore square root of 4 squared plus 3 squared, right? That should give you 5 meters. Don't forget the unit. Right. And I'll put some more space to solve for the angle. Okay. So to solve the angle, okay, why do we want to solve the angle? Because displacement is a vector quantity, so you need to indicate the direction as well. And that angle, the direction is given by that angle theta there. So it's a right-angled triangle. So trigonometry gives us a relationship between the sides and the angle of the right-angled triangle. Tangent theta is equal to the sides opposite the angle divided by the side adjacent to the angle. Okay. So the side opposite the angle, that's 3 meters, and the side adjacent to the angle is 4 meters. So that will be 3 divided by 4 for the tangent theta. You want theta, so you have to remove the tangent by doing an inverse tangent of 3 divided by 4, should give you an angle of 36.9 degrees. All right. Okay, so next one. Oh yeah, so that's something I would also suggest you put in your formula sheet, is the trigonometric relationships to find the hypotenuse, Pythagoras theorem, and then the angles. Tangent theta is side opposites over side adjacent. Sine theta is side opposite over hypotenuse. Cosine theta is side adjacent over hypotenuse. Yeah, and you can pick out the equations from the slides. Right, for the next question, a toy train accelerates from 0.10 or 0.1 meters per second to a maximum velocity of 0.35 meters per second in 0.15 seconds. And you want to calculate the acceleration of the train. Okay, so you're given the initial and final velocities and the time. Okay. There's nothing stopping you from using the kinematic equations here, of course, because kinematic equations relate the quantities. But you can also just use the definition for acceleration. Acceleration meaning the change in velocity over change in time. That's Vf minus Vi over the time interval. Okay. You're given the maximum acceleration and the minimum acceleration. So that will be Vf of 0.35 meters per second minus a Vi of 0.1 divided by the time interval. So you can always say that Ti is 0. That's the start point of the motion where you have Vi, so that the Tf is just the 0.15 seconds for the time interval. I'll just remove the unit, and you can just say Ti is 0. So you can have you'll have an acceleration of 1.7 meters per second squared. Okay, next question, how far will the train travel in 3 minutes after reaching maximum velocity, assuming that it travels at constant velocity? So here, you know, the time is given 3 minutes. If you convert that to seconds, you have to multiply by 60 because 1 minute is 60 seconds. There's 3 minutes. So you have to multiply with 60 seconds 3 times. 180 seconds. And then you're given that it reaches maximum velocity, which is from the previous question, 0.35 meters per second. Yeah, V, let me just use V. And you want to find how far it will travel, delta X. Okay. Right, so we know position is related to velocity via the change. So velocity is the change in position divided by the time it takes to cover that distance that's traveled. It's how far the car will travel. Right, but we need to rearrange this equation because we want to find delta x, not v. So if I multiply both sides with delta t, okay, notice you have delta x is tied with delta t via the division sign. So you have to do the reverse operation, which means you have to multiply in order to cancel out the delta t. Okay, so doing that, multiplying with delta t cancels out delta t on the right side. And then you have there an equation now for delta x is velocity times the time interval. And you know everything. You know the velocity and you know the time. So delta x is equal to 0.35 meters per second times 180 seconds. Okay. Be careful with units. Your units should always be consistent. So it's good practice to convert to base units if you're given other units like minutes or hours. So that will give you a distance traveled of 63 meters. Okay. Right, so for motion problems, first, before you go and look at kinematic equations, try to see if you can solve the problem using the basic definition of acceleration and velocity first. Because of course those are simpler equations compared to kinematic equations, like here. So kinematic equations are these 5 equations that relate 4 variables together. But I would suggest, before going to kinematic equations, try to see if you can answer the question just using the definitions for velocity being equal to change in position over change in time or time interval, and the definition for acceleration, where acceleration equals change in velocity over change in time. Okay. Right. So the next question here, so I've put down the kinematic equations before question 7 in this worksheet, because then we'll be looking at kinematic equations now. Starting from rest, a ball rolls horizontally on the ground with a constant acceleration of 4 meters per second squared. What is the ball's speed after 8 seconds? Okay, so what are we given? Starting from rest, that's a clue. Initial speed is 0. Constant acceleration, so this means acceleration is a. And then we're being asked, what is the ball speed after 8 seconds? We're given the time. Right? Okay, so try to see if you can solve this question using the definition for acceleration. So you're given the acceleration, you're given the initial velocity, initial speed, and then you're given the time, and you want to find the final speed. And you know acceleration is related to velocities, final velocity minus initial velocity divided by the time interval. Okay, so just from the definition of acceleration, you can actually already solve the problem, because you're given the initial velocity, you're given the time, and you're given the acceleration. You just don't know what is the final velocity. But you simplify this, your VI, your initial velocity is 0, so you're just left with VF on the right side divided by, you can just say time. Okay? Putting TI is equal to 0. So you just, the time is just 8 seconds, which is the final time. You want VF, so you have to get rid of time which is it's VF is divided by time. So you get rid of that division by multiplying both sides with time. That eliminates time, and therefore your VF is equal to acceleration times time. Acceleration is 4 meters per second, and time is 8 seconds. So that gives you a VF of 32 meters per second. Okay. Right, so you can solve this question using the definition of acceleration in relation to change in velocity with respect to time. But let's solve this problem using the kinematic equations, because in the test it's multiple choice, and sometimes we'll specify, we'll ask you specifically to identify the variables that are given, and therefore pick out the kinematic equation that you will use. So in that case, then you fill out this table. We said that the kinematic equations relate all the variables that describe the object's motion, right? Okay, and there are 5 variables that describe the object's motion: delta x, vi, vfa, and delta t. So make this table from what's given. Delta x is not given. Okay, we don't know what's delta x. There's no information about delta x, so we don't know that. Vi, it's implied. Vi is 0 because your object starts from rest. VF, that's what we want to find. What's the ball's final speed? Okay, acceleration is given 4 meters per second squared. Okay, and the time is given 8 seconds. Right. Okay, by filling out this table, you can then go to your kinematic equations and pick out which equation to use. Right. So which equation can we use to solve for VF? Let's say this is kinematic equation 1, 2, 3, 4, 5. Which kinematic equation will be useful for us? Yeah, good. We don't know delta x. Okay, so anything that has delta x will be of no use. So you're right, the only equation is VF is equal to VI plus A delta T. Okay. You'll actually find that this is actually the definition for acceleration if you rearrange it. Acceleration equals VF minus VI over delta T. But then you can straightforwardly solve for VF. VI is 0. A is 4. And time is 8. You should get the same answer for VF. Okay. So in questions, you'll see if you go to the practice test, you'll find a question like this, which says identify the variables that are given, identify the information that's given in the problem. Be careful with such kinds of questions because there are some values that are implied. So for example, here we say that it starts from rest. So we don't explicitly give you VI is equal to 0, but you should be able to pick out that VI is 0 from that expression starting from rest. So you should include that as one of the variables that is given in the problem, even if we did not explicitly say VI is equal to 0. Okay, next question. How long will the ball take to reach a speed of 36 meters per second? Okay, this time we want to find how long, delta t. So again, you have your variables, delta x, vi, vf, a, and delta t. Delta t, that's what we want to find. Right, acceleration We know that to be 4 meters per second square. It's the same problem, so you can use the same values. 32, we have the extra information now because we solved that from previously. And then VI, we're starting from rest, so that's 0. Delta X, we still don't know. It's still not given here. So if we were to find delta T, anything that has delta X, we cannot use again. So it's still, again, the first equation that will be useful, but we need to rearrange that to find delta T. So you have VF is equal to VI plus A delta T. We did the rearranging of this in the first question. Okay, so I won't go through the rearranging in detail, but delta T VF minus VI over A, that's the rearranging that we did in the first question. Right, so your VF 32 minus 0 divided by 4 gives you 8. Yeah, so let me just 32. Yeah, 8. Oh, 30, sorry. Yeah, that's why I was wondering. So the question says, how long will the ball take to reach the speed of 36 meters per second? So our VF is not actually 32 from what we solved, but it's given to be 36 meters per second. Yeah, I'm sorry for that oversight. So your VF should be 36 meters per second, which is what's given in the problem. Because otherwise we'll just get the time from the previous question. So the time it takes to reach a final speed of 36 meters per second is 9 seconds. Right? Okay, next question is a free fall question, and you will see why later on. So you accidentally drop your camera while taking pictures on top of the Leaning Tower of Pisa, sorry, and from rest. So again, keyword there, from rest, it falls vertically downwards, hitting the ground after 11.5 seconds. And it says neglect air resistance in your calculations. So whenever you see air resistance is neglected, that's when you know that it's a free fall problem. Okay, yeah, that's the defining phrase that will give away the clue that it's a free fall problem, because we don't usually tell you it's a free fall problem. It's part of what we're testing, right? If it's for you to determine whether it's a free fall problem or not. But reading something like neglecting air resistance, that means it's a free fall problem. And free fall problems use kinematic equations, except that the motion is along the vertical instead of along the horizontal. So still do the same strategy as we do in kinematic problems. Okay, write your information table of facts or table of information based on what's given. So you're starting from rest, that means VI is 0. Okay. What's this? Time, 11.5 seconds. It's given. VF, there's nothing about VF here, so that's not given. How high is the Leaning Tower of Pisa? That's actually what I want to find. What's the acceleration in this case? Okay, can I sort of pick out from the problem what the acceleration of the camera that dropped is? Yeah, very good. It's negative 9.8. Yeah, it's a free fall problem. In free fall, the acceleration is constant. It's because of the gravitational pull of the Earth, and it's always downwards. That's why it's a negative acceleration, and the constant number is 9.8 meters per second squared. Okay, so it's very common when you look at the practice test, free fall problems will almost definitely always be there, because first we want to test whether you can pick out that the problem is a free fall problem, and then from there we want to test whether, if you know that in free fall the acceleration should be always negative 9.8 meters per second squared. So usually we give you very little information in terms of the actual numbers that you can see in the problem, but there's actually more information that you can pick out, like acceleration is always negative 9.8, and then from rest, that's 0. Yeah. So looking at your kinematic equations, it's VF we don't know. Okay, so let me erase this. Any equation that contains VF cannot be used. That's not appropriate. Equation 3, 4, and 5. So there's really just only one equation that we can use. Is there anything else? Nope, we don't know VF. Yeah, so we'll just take note of that equation. It's that long one, VI delta t plus 1/2 A delta t squared. Oh, what? Go away. How do I remove this? Yeah, okay. Whew. Right, so we want delta x, and that's the only equation we can use, VI delta t plus 1/2 A delta t squared. Okay, VI is 0, anything we multiply with 0 is 0, so we have just 1/2. Okay, A, be careful here, make sure you include the negative sign, so times negative 9.8. Okay, and then times the time 11.5, and don't forget there's a square. You have to raise that to the power of 2. You will find you will have a negative answer for your delta x, negative 648 meters. Okay, what's the negative sign? What does the negative sign in delta x mean? It means that it's a downward direction. So the displacement is downwards. The direction is downwards. Okay. Right, next question. At what speed will the camera hit the ground? So we now have to solve VF, which initially we don't know, and now that's what we want to solve with the extra information about delta x. Okay. Right, so we now have a lot of options. So let me just use the same, maybe so it's neater. So delta t is still 11.5 seconds, a still negative 9.8 meters per second squared. Vf is now what we want to find. Vi is still 0. Delta x is negative 6.48 meters from the previous question. So make sure to include the negative sign as well. Okay, looking at our kinematic equations, we want to find Vf. Okay, so that's our kinematic equations there. You can use several equations to solve for Vf. I would suggest using one that you don't have to rearrange. And so maybe, yeah. If I were you, I will use equation 1. Let me just tidy up. Right? Okay, if I were to choose, I will choose equation 1 because I don't have to rearrange anything. It's all already given in terms of BF, and I know everything else. Technically, equation 3 is also quite easy. It's just BS squared, but remember that whatever you get, you have to take the square root of that. So let's just use equation 1, shall we? It's the simplest one, VI plus A delta T. Vf is equal to Vi plus A delta T. Vi is 0. Okay. Again, negative 9.8. Remember to include that negative times 11.5 gives you negative 113 meters per second for Vf. Okay. The negative sign again gives you the direction. And the convention we use is negative is downwards. Okay. Cool. Right, moving on. It's a football that kicks straight up from the ground with an initial velocity of 20 meters per second, neglect air resistance. So here again is that phrase neglect air resistance, which means it's a free fall problem. And you'll see, because it's a free fall problem, very little numerical values are given. In fact, only one is given, which is the initial velocity of 20 meters per second. Okay, let's go back here. Okay, let's see. Let me try to put that in the calculator. So we have 11.5 squared times 9.8 negative times 1/2. It's 648 meters. So make sure you did the square. Yeah, it's squared. Yeah, be careful. It's squared. So it's delta T squared. Yeah, no, it's all good. But usually, yeah, the square is easy to overlook. So be careful with the squares when putting numbers in the calculator. Okay, so let's go back to question 9. It's a free fall problem. And what we're only given is the initial velocity VI. So that's VI is 20 meters per second. And we want to find the maximum height. So again, free fall problem is a kinematic equation problem. So I would really recommend filling out this table of facts. It makes it makes things simpler. Initial velocity is not 0 this time, it's 20 meters per second. Okay, it's free fall. So just like before, acceleration is 9.8 meters per second squared. So that's, we almost always don't give you the acceleration, the negative 9.8 meters per second squared in such a free fall problem. It's up to you to find to put that by yourself. Right. What else do we know, or at least infer from the question? Delta x, that's the maximum height. That's what we want to find. Okay, a delta t, there's nothing about time, so we're not given delta t at all. How about VF? Do we know VF, or is there a way of finding what VF is? Because otherwise we only know two things, VI and A. And whenever you're using kinematic equations, you need to know at least three things. So can we know what VF is? Or at least can we deduce from the problem what VF we should use to solve for delta x? Any idea what VF should be? Yeah, conceptually it should be 0. Yeah, because the ball is kicked upwards, it will go up. Okay, it will eventually come down, right? Anything that goes up will come down. Before coming down, it should momentarily stop. Yeah, when it stops, the velocity is 0, and then it will come down. Right, and by dividing the free fall scenario into two parts, the one where the ball's going up as the first part and the one where the ball's going down as the second part, then we can say that in the first part of the ball's motion going up, the final velocity is 0 at the peak or at the top of its motion. Right, so then we can say that it's 0 meters per second for the final velocity at the top. We're just looking then at this motion here going up, where VI is equal to 20 meters per second and VF is 0 meters per second, right? Yep, we'll solve for the maximum height. So we don't know delta t. It's one thing, and we know VI, VF, delta t. So looking at your kinematic equations, which equation should you use to solve for delta x? Yeah, anything that has delta t won't work because we don't know delta t, right? So there's only equation 3 that works to find delta x. VF squared is equal to VI squared is equal to, VF squared is equal to VI squared plus 2A delta x. We rearrange this equation to isolate delta x. Okay. Right, if we subtract both sides, we subtract VI squared from both sides. Okay, that removes VI squared from the right side of the equation. And you have VF squared minus VI squared on the left is equal to 2A delta x. Okay, then we divide both sides by 2A. That gets rid of 2A on the right side. So we have delta x. So let me just flip this equation, VF squared minus VI squared divided by 2A. Okay. VF squared is 0 at the maximum height. Initial velocity was given to be 20 meters per second. Don't forget there's a square. Okay, so don't forget, yeah. to square your VI and divide that by 2 times. Again, don't forget your negative in the 9.8 meters per second squared. And that should give you a delta x, a positive delta x in this case, because you have negative signs on both sides there. The fact that you had a positive delta x means that the ball, the displacement of the ball is upwards, right? And the maximum height is actually upwards relative to the starting position of the ball. So a positive answer would be sensible in this case, right? Okay, the next question, how long will it be airborne before it hits the ground? So you want the time now, okay? So it's the time for the whole flight. So the time it takes the ball to go up and go down to the original position before it was kicked upwards, okay? Right, so there are 2 ways of doing this. You can either, you can either again look at 2 parts of the motion, look at the going up part and then going down part as 2 different parts of the motion, or you can look at the going up and down as one whole motion. But if you're looking at going up and going down as one whole motion, then your VF would be at this point. VF will be at this point for the whole motion. If you're just looking at the first part, like we did in finding the maximum height, then VF is equal to 0. Otherwise, if you're looking at the whole motion, then VF will be here, which is negative 20 meters per second. So I think to make it simpler, let's just divide this into 2 parts again and just look at the time it takes the ball to reach the maximum height, okay? And solve for the time it takes to have to reach this maximum height where VF is equal to 0. Okay. So time to reach maximum height. Maximum okay, my pen should cooperate. Maximum height. So we already now can use delta x 20.4 meters from before. VI was also 20 meters per second. VF will still be 0 because then it's the maximum height, the first portion of the trip we're looking at. Acceleration is still negative 9.8 meters per second squared. And delta t is what we want to find. Okay. So we're spoiled with choice. We know 4 variables, where's the kinematic equations, and we want to find delta t. Okay. All right, I would try to stay away from, you have delta t squared, and the equations look a little bit complicated. You have to rearrange that to isolate delta t, and you have a delta t squared in equation 2 and equation 5. So maybe you'd want to steer away from that. So what equation do you want to use? Of course, equation 3, you cannot use that. It doesn't have delta t. So which equation do you want to use? It doesn't really matter whether you use equation 1 or equation 4, because, you know, we know the acceleration, we know VI, we know VF. So how about we use equation 1? Okay, are you happy to use equation 1? Vf equals Vi plus A delta T. Okay, let's use equation 1 to solve for delta T. Okay, because we already rearranged this earlier, I think. Yeah, subtracting both sides with Vi and then dividing by A. Right. Okay, I think we already rearranged this. I think we rearranged this to isolate A earlier. So the rearranging is the same, except that instead of dividing by delta T, we divide by A. So I won't go through the detailed rearranging for that. So the VF is 0 at the maximum height, minus 20 meters per second for the initial velocity, and then acceleration negative 9.8. You should end up with a positive time. There's no sense to have how do I, yeah. So delta T should be positive 2 seconds. Okay. So this is the time it takes to go up. That's why VF is equal to 0, because we're just looking at the going up motion. But the problem asks for the time for the entire duration. So total time should be twice, 2 times delta T, or 4 seconds for the entire trip. Right? So that tells you the time it takes to go up is equal to the time it takes to go down. That's why we just multiply by 2. Right. Next one is motion graphs. We have here a velocity time graph. The graph there is the blue line. And we are asked to describe the motion of the flight in terms of velocity and acceleration during each trip. Okay, so we need to divide this from 0 to 2 seconds. The graph is linear, it's straight and going up. And then from 2 to 10 seconds, you have a different pattern. So the velocity is just a horizontal line. And then from 10 to 12 seconds, it's straight or linear and going down. And from 12 to 16 seconds, it's a horizontal line. So we divide the graph into these segments, 4 segments, and describe the motion. So from 0 to 2 seconds, okay. So from 0 to 2 seconds, you have the B is moving with positive velocity. Meaning positive direction and increasing speed. Yeah, right. Increasing speed because at one point it's moving at 1 meter per second, and then 2 meters per second, 3 meters per second, and so on, right? So it's moving with increasing speed, but the interval for the speed is constant. That means that the acceleration here will be a constant positive and constant. So if we actually plot the graph of acceleration versus time, acceleration in meters per second squared versus time in seconds. Okay, from 0 to 2 seconds, you see that the graph is a straight line and that's going up. If you get the acceleration, if you want to find the acceleration from a velocity time graph, do you find the slope or the area under the graph? Given a velocity time graph and you want to find the acceleration, should you solve for the slope or the area between the horizontal axis and the graph? Slope, right? Okay, so if you were to get the slope of this straight line from 0 to 2 seconds, that will be a positive slope. So that will be a positive acceleration that's constant. And then from 2 to 10 seconds, the velocity is constant, and we know acceleration is change in velocity. Because the velocity is not changing, then your acceleration is 0 from 2 to 10 seconds. So the acceleration here is positive from 0 to 2, and then acceleration is 0 from 2 to 10 seconds. And then from 10 to 12 seconds, 10 to 12 seconds, you have this graph that's straight and going down. If you get the slope of that, you'll get a negative acceleration, because if you see again, the velocity is decreasing. So your final velocity is smaller than your initial velocity. So you'll get a negative acceleration between 10 to 12 seconds, a negative acceleration right there. And then from 12 to 16 seconds, so say this is 16 seconds, you again have a constant velocity. That means that the acceleration is 0 because your velocity is not changing. Okay. Right, so from 0 to 2 seconds, increasing speed and positive constant acceleration. From 2 to 10 seconds, you have constant velocity and 0 acceleration. Right. Let me just have some more space. Okay. And then for 10 to 12 seconds, you have a decreasing speed. Okay, you have velocity, the line is going down. So you have decreasing speed and negative acceleration. And then finally, from 12 to 16 seconds, you have constant velocity, 0 acceleration. Right? So that's how we describe the object's motion as given by the graph. And the next question asks us to explicitly calculate the acceleration of the bee during 10 to 12 seconds. And as I've asked earlier, and Anato answered, given a velocity time graph, the acceleration is the slope. But we need to get the slope between 10 seconds to 12 seconds interval. So 10 seconds, let me tidy up our graph. Okay, 10 seconds to 12 seconds interval is this one. Yeah, the downward sloping graph. Yeah. So you consider your starting and end points. Okay, to get the slope, you need the final velocity, the initial velocity, the final time, and the initial time. So seeing here, this will be your final time, and you're going from 10 seconds. So that will be your initial time. right? At the final time, the point is here. So that means your final velocity is 4. That will be your final velocity, and your initial starting point is at t equals 10. So that will be your initial velocity VI. Right. So 8, 4, 12, and 10. So then you can solve for your acceleration. It's the slope, or it's also VF minus VI over TF minus TI. Okay. VF, I forgot, sorry. So VF, it's 4 meters per second. VI is 8. Okay. 4 meters per second minus 8 meters per second. And the time is 12 seconds minus 10 seconds. Okay. That should give you a negative 2 meters per second squared acceleration. And the negative sign means that the slope should be downwards. And as you can see from the graph, the slope is indeed downwards. So that confirms the negative sign that you got in your calculation. Right? Okay, calculate the average acceleration during the whole trip. So 0 to 12 seconds interval. Okay. So it's for the whole trip. Okay. So let me tidy up our graph. Okay, 0 to 12. Oh, is it just 0 to 12? It's not the whole trip then. It's just 0 to 12 seconds. So it's actually just until here. Starting point 0 seconds, and then end point is at 12 seconds. Okay. Right. So there are two ways of doing this, and they're the same. The concept is actually the same. So you can use the definition acceleration equals VF minus VI over TF minus TI. That's actually what I used in finding the acceleration between 10 to 12 seconds earlier, because then you can just pick out this is the final point and this is the initial point. And you can pick out in your graph what your final and initial velocities and times are. So this will be VF and this will be VI. And of course, this will be TF, 12 seconds. Okay. Or the other thing is you can connect these 2 points. Connect these 2 points and find the slope of this line. Slope of this line will give you the acceleration. But you see that to get the slope of this line, you would still need to consider 2 points. And you can consider the end points of this slope. So in essence, you still need to find VF, VI, and TF, TI. Right. So let's find the acceleration from 0 to 12 seconds. So VF is 4, VI is 0 meters per second. Right. VF is 4 meters per second, VI is 0, TF is 12 seconds, TI is 0. 0.33 meters per second squared. Okay. Right. Okay. Next question, instantaneous acceleration at 1 second. Instantaneous acceleration, that's the acceleration at a particular instant of time. At 1 second. Okay, let me tidy up our graph again. At 1 second, it's this point that's 1 second. So we want to find the instantaneous acceleration at this point. Okay. When you solve for the acceleration, you need at least 2 points, right? You need the final velocity and the initial velocity, and you need the final time and the initial time. So it's useless. Yeah, that's okay, Oksana. I realize it's getting long, but yeah, have a good weekend and I'll see you next week. Right. So yeah, we need at least 2 points to find the acceleration. And that's where we need to draw a line that's tangent to this point where we want to find the instantaneous acceleration. Okay, and if the line, if your instantaneous acceleration falls on a straight line, then the tangent is the straight line itself. And you can just get the slope of this straight line, and that will be equal to the instantaneous acceleration. So let's get the slope of this straight line from 0 to 2 seconds. Okay, but we can just take any point along the line. So let me take these 2 points between 0 and 1 second, so that 4 meters per second will be my VF. Okay, 0 will be my VI. 1 second will be my final time, and initial time will be 0 seconds. And let's find the acceleration. So VF is 4 and 0 and 1. So VF is 4. Four minus initial is 0. Final is 1 second, because that's where we determined VF from. Okay. VF is 4 meters per second when the time is 1 second. And that's why your TF should be 1 second here. And that gives you 4 meters per second for the acceleration, the instantaneous acceleration. Okay. Right. And then next, we want to find the net displacement of the B. Okay, so net displacement, yeah, given a graph of velocity versus time, it's either just slope or area under the graph. And we've been working with the slope to find the acceleration. So therefore, to find the displacement, we need to find the area under the graph, right? And it's the net displacement, so it's for the whole duration of the motion. Okay. So again, I'll tidy up our graph here. Okay, so our graph is bounded by this blue line. Okay. Area under the graph means the area between your graph, the blue line, and the horizontal axis. So that means we actually need to get this whole area. We need to figure out, okay, what is this whole area right here? Right. It's irregularly shaped. Okay, how do we solve for the area? We need to divide this whole area into triangles or rectangles or trapezoids. Okay, so trapezoids would probably give us the smallest number of sub areas that we need to solve. So we can divide this into 2 trapezoids. So if I divide this here, okay, that's our graph. And then this second area is that. Okay, so we've divided the whole area into two trapezoids. So a trapezoid is a geometrical shape where you have two sides that are parallel and two sides that are not parallel. Okay, the two sides that are parallel, we call that the bases. Oh, what? Okay. Oh, yeah. Okay, so this is base 1 for the trapezoid. This is base 2 for the trapezoid, and this is the height of the trapezoid. Okay, for the second trapezoid, you have, let's say that's base 1, base 2, and the height is the distance between two bases. Okay, and the area of a trapezoid is equal to 1/2 times the height times base 1 plus base 2. Okay. Right. Okay, since we have the figure here, maybe I'll just do the working out of the solution to have space. Yeah, I'll just have to erase this bit here. Okay. Right, so we find the area of trapezoid 1. Let's say that's area 1. Let's say that's trapezoid 1 and that's trapezoid 2. That will be 1/2 times the height. Okay, the height goes from 4 to 8, so that will be 4 meters per second. Okay. Times base 1 plus base 2. So base 1 goes from 10 seconds to 2 seconds, so that will be 8 seconds, plus base 2 goes from 12 seconds to, that's about 1 second. So that's a length of 11 seconds for base 2. Right, so that will give you an area for trapezoid 1 of 38 meters. Okay. The area will give you displacement, and that's measured in meters. Okay, the area for the trapezoid 2 is 1/2 times the height. The height, it goes from 0 meters per second to 4 meters per second. So that should be 4 for the height, times base 1. Base 1 goes from 16 seconds to 1 second. So that will be 15 seconds for base 1. And then base 2 goes from 16 seconds to 0. So that will be a base of 16 seconds. Okay. Right. Okay, doing the calculation, 15 plus 16, that's 31 times 4 times 1/2 gives you 62 meters for the area of trapezoid 2. So the total area will give you the net displacement. Right, so your net displacement will be 38 plus 62 meters, which is 100 meters for the net displacement. Right? Okay. Of course, there's nothing stopping you from using triangles and rectangles. But I just find that if we did triangles and rectangles, we'll have a lot of triangles and rectangles, maybe at least 1, 2, maybe 2 triangles and 2 rectangles. And that means you need to calculate 4 areas. But yeah, doing trapezoids maybe simplifies things sometimes. Okay. All right. Okay, we're nearing the end. Realize it's quite long. Yeah, so we've worked out the net displacement above. So this is the last question. It's on forces. Okay. The picture below shows a man who's pulling a boat to the right across the beach. We are given here a corresponding free body diagram acting on the boat. So the object is the boat, and we have questions in relation to the forces acting on the boat. So first one, label the free body diagram by correctly identifying the forces that are acting on the boat. Okay, so what's the force that's downwards? What is this force? This downward force. Weight, yeah? Okay, it's the easiest force that you can draw on a free body diagram. Anything that has mass has weight, and it's always directed downwards. What's this force that's vertically upwards? Yeah, normal or support force. It's the normal force vertically upwards. Okay, what's this 146 Newton force that's to the left? It's against the direction of where the man is pulling the boat. So you're right, that's the frictional force, correct? Okay, and then you have these 200 Newton force that's at an angle. You can just name that as pull force or tension force if it's via the string. Okay, so you have the tension force at an angle of 20 degrees. Okay. Then it says calculate the net force acting on the boat along the x-axis. So x-axis is the horizontal axis here. Tension force is diagonal. So whenever you have a diagonal force, you can be sure that you have to break that down into vertical and horizontal components. Okay. Horizontal component for the tension and vertical component for the tension. So this black line, and that's at an angle of 20 degrees. Right? So just check if your angle is measured relative to the horizontal, then the x component will use the cosine theta function. So your x component will be t cosine theta. Okay. Since theta is with respect to x-axis. Right, tension force is given 200 newtons, angle is given 20 degrees. Okay, so we can get the tension force. So cosine 20 times 200 is 187.9 newtons. Okay. Right, and it's pointing to the right, so it's positive. But you have a frictional force that's pointing to the left. So the net force along x should be the x component of tension that's positive minus the frictional force that's negative. Yeah. All right, so you have 187.9 minus 146 will give you 41.9 newtons. Let me just quickly check that. 187.9 minus, yeah, 41.9 newtons for the net force along the x. Okay. And you need that net force to calculate the acceleration of the boat that has a mass of 50 kgs. Okay, so when you're asked about acceleration in relation to forces, it's Newton's second law of motion. Force is equal to mass times acceleration, or acceleration is equal to force divided by mass. Okay. So that's Newton's second law of motion relating the force to the corresponding acceleration experienced by the object. So along the x-axis, you have a net force of 41.9 newtons, which we solved earlier. Okay. Yeah, net force, to have the more complete definition, divided by the mass, which is 50 kgs. Okay. Gives you an acceleration of 0.838 meters per second squared. Right. Okay, next question, calculate the normal force exerted by the ground on the boat. So in our free body diagram, it's this upward vertical force that we want to find. And yeah, when we're doing Newton's second law of motion with net forces, we look at one axis at a time. So like in finding the acceleration in question C, we were just looking at the x-axis, the horizontal forces, the forces along the horizontal. Now, when we're looking at the normal force, and you want to find the normal force, because the normal force is vertically upwards, that means we have to consider all the forces along the vertical, and there are only two forces along the vertical. There are three. There are three forces along the vertical, right? You have the y component of tension force. This is actually y. Yeah, the y component of tension force, you have the weight force and the normal force itself. So you have three forces along the y-axis. And the boat is not moving along the y. That means the net force along the y should equal 0. Okay. So F net, okay, along y-axis, along the y-axis, you have the normal force that's upwards. Okay. You have the y component of the tension force that is also upwards. And then you have, the weight force that is downwards. And the net force should equal to 0 because your object's not moving up or down. Or you can also say that the upward net force should equal downward net force. Okay. So you have two upward net forces, normal plus tension, should be equal to the weight force. Okay. Right. We want to find the normal force, so we rearrange this equation to isolate normal. The normal force is tied with the y component of the tension via this plus sign. So to undo the plus sign, we need to do a minus. If we minus with ty, we eliminate ty on the left side, but we also have to minus ty on the right. Okay. So ty minus ty is 0, and we're left with just normal force on the left side. That's equal to weight minus ty, y component of tension on the right side. Okay, the weight force, the mass is given as 50 kilograms. The mass of the boat is given to be 50 kilograms. So we can calculate the weight force. Weight force is mass times G. Weight is 50 kilograms times 9.8, gives you 49 newtons. Quick check. 50 times 9.8. Yeah, 490 490 newtons. And then for tension Y, that's tension sine theta. That's what we, yeah. Oh, we solved TX earlier, but Y component is this vertical component opposite the angle 20 degrees. Okay, but since the angle is measured relative to the x-axis, then to find Ty, that will be a sine theta function. So that will be T sine theta, 200 sine 20 degrees. Sine 20 degrees times 200, 68.40 newtons. Okay. Then you'll be able to find your normal force, 490 minus 68.40. Will give you 421. Okay, did I make a mistake here? I think I did, because the sign of Ty, yeah. Yeah, I thought I did make a mistake. So Ty is downwards. Ty is downwards. Okay. So Ty should actually be negative. Yeah, sorry about that. Ty is downward, so Ty should actually be negative. And your upward force is actually just the normal force. It's just the normal force that's upwards, and you have the weight force plus Ty that's downwards. Yeah, sorry about that error in the sign for Ty. So we have to add instead of subtract. 5. Yeah, 558.4 newtons, or just 558. All right. Okay. Whew. Last question. Oh, the second to the last. So identify an action-reaction pair in this scenario. There are many. And we'll just, yeah, you can just choose two. So action-reaction, just choose two objects and then their interaction. So for example, the man is pulling on the boat. Okay, that's your action force. The reaction force will involve the two same objects, the man and the boat, but just reverse the direction of the force. So say the action is the man pulls on the boat to the right. Okay. The reaction force for that action force should also involve the man and the boat, but you reverse the order so that you reverse the direction, and you say that the boat pulls on the man to the left. Right, so first identify two objects that are interacting with each other, say the man and the boat, and then write down the interaction. The man pulls the boat with the direction to the right. For the reaction force, just invert the two objects and then reverse the direction. So the boat pulls on the man, and then the direction is to the left. Okay. Right. And finally, if the boat was brought to the moon, where g is 1.62 meters per second squared, gravitational acceleration g, what would be its weight and what would be its mass? Okay. Right. So differentiating between weight and mass. Earlier, we calculated for the weights of the boat here. Okay. Weight is the force that you multiply, where you multiply the mass with gravitational acceleration. Yeah. So weight is mass times gravitational acceleration g. The mass is 50 kilograms. Now the new g is 1.62 meters per second squared. So the new weight should be 81 newtons. Okay. So notice how the weight makes use of the mass, okay? And the weight is measured in newtons, and it depends on the gravitational acceleration. It depends on where the object is. Mass doesn't change. It's 50 kilograms. It doesn't change regardless of where the object is, regardless of what the gravitational acceleration is. The mass is always the same, assuming that the object is intact and it doesn't lose any of its atoms that make it up. So the mass is an intrinsic property of the object measured in kgs. All right. Okay, but I hope that by now we've been calculating weight many times now. I hope you're now able to distinguish between weight and mass at this point. Okay, so this ends, that's all of the questions in the revision worksheet, and that pretty much covers the topics for the test, except for the torque. The torque bit, there are no questions about the torque here. But I think our lecture 9 slides and the worksheet for lecture 9 should be sufficient, and it's hopefully it's relatively fresh at this point. Yeah. So is there any other question you want us to look at, or specific topic that you want us to look at? Okay. I realized we've been here for over an hour and a half, and yeah, kudos to all of you for sitting through an hour and 50 minutes of me just talking. But I hope it helped for the revision. Okay, right. You're welcome, Nikita. Okay, I think we should end the session here. I think it's been pretty long. I encourage you to go through the practice test on stream, and of course, feel free to ask me if there are tricky questions. Yeah, you can take a screen capture or photo of the problem you're working out and email it to me, and then we can discuss that by email, or you can set a revision session with me. Any is fine. But yeah, if there are no specific questions, maybe I'll let you go. I'll let you have a good weekend. Enjoy the afternoon sun. And I'll see you next week. Yeah. Cool.